Hello everyone. In this video we will be talking about volumes, computing them by cross-sectional area, and then also by the washer and disk methods. So the idea here is to basically extend what we've done for computing areas in 2 dimensions to move up to volumes, right? So we know that area under a curve we got by starting with the Riemann sum, right? We could put some rectangles under here. We sum up these areas, and then this gives us an approximation, right? And so we have basically the sum of our height times our width. And then when we take the limit, right, when we take these more and more rectangles that are thinner and thinner, then we get the integral, if this is from a to b, of f of x dx. And this is our area. Okay, so we want to try to do the same thing, but for a solid, a 3-dimensional object. Okay, so let's look at this 3-dimensional object here. So the first thing I'm going to do is just slam some axes on this guy and say, this is going from A to B. And so, again, we're not going to be able to do what we did before because rectangles are not going to fill up a 3-dimensional object. However, we can do the same general idea of slicing this up into sub-intervals here and then take volumes in between instead of areas in between, since we're trying to estimate volume. And so the most natural shape here would be a cylinder, right? So this is going to be kind of poorly drawn because this is not my skill. But we've got this little cylinder here, and we can just slice up with a bunch of different cylinders. Obviously our cylinder is going to be a little taller over here. And so when we add these all up, we'll be approximating the overall volume, right? And so what's the basic idea here? How do we generalize this? Because not everything is going to look exactly like this. Well, what we're doing is saying that our volume in general is approximately the sum of these volumes of slices. Right, and then how do we get the volumes of slices? Well, this width we can ensure, just like we did for rectangles, that it's consistent throughout. And so this is like our delta x. And then what we really need then is our cross-sectional area at each point. And so if this is, say, xi here, then we can rewrite this as some area function at xi. So this is just our cross-sectional area. So in this case, it would be pi r squared because we're talking about circular cross sections there. But if we're doing a pyramid, for instance, we could have square cross sections, in which case this formula is going to be different, times our delta x, right? Because our area times our height, or our width in this case, since I laid this down horizontally, is going to give us volume. And so then what does this turn into overall? Well, just like we did before, we take a limit. We take these to be really, really thin slices and as many as we can fit in there as possible. And it becomes an integral, in this case from A to B, of our cross-sectional area function times dx. So let's actually see what this looks like in practice. All right, so we're going to look at this 3-dimensional object. This is like a triangular cone here. So it meets down at a right angle down there. Our height is 10, and then we'll say that this bottom is an isosceles right triangle with side lengths 4, and it turns out we won't really need to compute the hypotenuse. So how do we figure out this volume? Well, one idea is first to put it on some axes, right? Get it so that we can end up setting up an integral here. So one way to do this is I can just put my point here from this, and so it's going to be length 10 and then height 4. So now you'll note, of course, that this is not 3-dimensional here, but it turns out that doesn't really matter because I capture the same thing on each side. So think about what these cross sections are. If I slice this horizontally here, right? So if I just travel up some height, then I'm going to, again, get a right isosceles triangle in here. It's just that as I move farther up, then I'm going to have shorter sides on my isosceles triangle, right? And so, laying this down on its side over here, what's going on? Well, I'm basically saying, hey, if I stop at x here, then how tall is this part? This is the side of the isosceles right triangle. And then if I want to figure out the area of a cross-section, well, this is my cross-section, right? And so my area function, my a of x, my cross-sectional area, is 1/2 base times height. But this is isosceles, right? And so it's just going to be the same for the base and the height. So let's go ahead and actually figure this out. So what we can use here is similar triangles, right? So we're looking for this height, call it h here. So h over 4 is going to be the same as x over 10, just because we have similar triangles. And so we've got 10h is 4x, and we want to solve for h, right? And so this is going to be 4/10 or 2/5 x. And therefore our area function at x, the area of this cross-section, is going to be 1/2 times 2/5 x squared, because the base and the height are the same. And so that's 4/25 and thus 2/25 x squared. So now the way I've done this, right, since this is length 10, I'm just integrating from 0 to 10 because I'm going along the x-axis here and just adding up these cross-sectional areas infinitesimally thin to get my volume. And so my volume is going to be the integral from 0 to 10 of my area function, 2/25 x squared dx. And so when you actually do this out, right, you're going to get 2/75 x cubed from 0 to 10. And so you get 2075 or 80/3, whatever's cubed, right, because it's volume. All right, so for your first exercise, I want you to set up, you do not have to solve, the integral to compute the volume of a right circular cone of base radius 6, right? So this radius here is 6 and height 8. Okay, so again, think about what your cross sections are at a general x here and find that area in order to set up your integral. All right, so now we're going to introduce the disk method. So this is specifically for volumes of solids of revolution. So what do I mean by this? Let's take the graph y equals x squared. Okay, so looks something like this. Let's say we'll go from 0, 0 to 3, 9. So we've done area under a curve before, right? So we can just integrate x squared from 0 to 3, and that would be this area. But if we want to get a solid, we can actually revolve this graph, revolve this region here that I've shaded in red, around the x-axis. Okay, so if you go around the x-axis here, then what you end up getting, right, is something that looks like this. Right, you've got your x squared graph here, and then it just kind of flips over and goes around. So now we have a solid, first of all. So how do we get our area? Well, we can basically use the idea before, except for, in this case, we know what our cross-sections will always be whenever we're rotating around an axis, right? We see that these are definitely going to be circular cross-sections. And so in that case, right, in general, we want something like a to b of our a of x dx. But in this case, we know this guy is going to be pi r squared. And even better, we know what our r is here, right? Because how are we getting our radius? Well, any circle, any cross-section here has radius, this part here, right? Which is exactly the height determined by the value of our function. So our r is actually equal to x squared here. And so this becomes a very simple integral, right? So this specific case, if I want to look at this one, it's 0 to 3 of pi times x squared squared dx. And so then, of course, you can just go ahead and do that out. And so it's pi x to the 5th over 5 from 0 to 3. And 3 to the 5th is going to be 243. So we've got 243 pi over 5. Now, this is not the only way that we could have rotated this guy. We could just as easily have rotated this region about the y-axis, right? And then we get like this bowl shape, right? Go down, and then we get this guy that we're calculating the volume for. Now this time, remember, just like area between curves, sometimes it's easier to do integration with respect to y. That's exactly the case here, right? So I mean, our volume is calculated the same because we still have circular cross sections, right? All of these cross sections here are circular. And how do I get my radius? Well, it's exactly the height, but from the perspective of the y-axis, right? And so y was equal to x squared. But in this case, since I'm looking for the positive one, I can solve x is equal to root y. And so my volume in this case is from 0 to 9, because I'm going up from 0 to 9 and doing horizontal cross sections. And then pi times root y squared dy. Okay, and so then this one, we just get pi y squared over 2 from 0 to 9, and so we get 81 pi over 2. Okay, so the disk method in general, what we just kind of saw, is that if we revolve around a horizontal axis, right, like the x-axis, or it doesn't even have to be that, it could be any horizontal line, then we're going to get vertical cross sections, right? So if you have this, revolve around this guy, you're going to have vertical cross sections, and you're going to be integrating with respect to x. And so this r of x is just your radius at x. And similarly, our r of y, if we rotate around a vertical axis, then we're going to get horizontal cross sections with respect to the variable y, and our r of y is the radius at height y. But in either case, right, we have circular cross sections, and thus are doing this pi r squared, where we just have to worry about exactly what our r function is. All right, and for your second exercise, I want you to go ahead and set up, but again, do not solve, the integral to compute the volume of the solid obtained by rotating the region under the square root of 9 minus x squared around the x-axis. For all of these problems, just as with the area ones, I highly recommend drawing a picture first and getting a picture of your region, an idea of what you're doing, and then go ahead and try to set up the integral. All right, thank you for watching.